Hello everyone. Today we are going to present on the topic social robot navigation. The team members are Nihal Sunil Nawale and myself Denny Bobby. Problem description and motivation. To prepare for a future where robots are more commonplace, it is important what behaviors people find socially acceptable. Past research shows that the robot should adhere to prevailing social norms such as those related to approaching people. There are over 30 million consumer robots worldwide. As robots start to be deployed in public spaces, it is important that their behavior is in line with the social norms that exist in the environment where the robots is to provide service. In HRI field, researchers have investigated elements of social robot approach behavior. Some of them are what distance to keep from people, from which direction to approach, what speed to approach. The human-robot navigation problem is not same as the problem where humans can be treated as normal obstacles. Robots should navigate differently around humans so that they don't feel awkward. In different countries, expect motion of robot in different ways. Some countries need slow and safe robots around humans, while the others need fast and proper proxemics robots. Motivation. So in motivation, it can be categorized into two components. One is collaboration between humans and robots while working, under which the examples are warehouse robots and mobile robots in industries. The second component is robots working in human environment. The examples for these are service robots. So here we talk about categorization and comparison. And the six papers which are discussed in this presentation is categorized based upon methods and applications. The first paper, which was published in 2013, uses Gaussian mixture model for Proximus and around group of humans. And the application was navigation around humans, like a single human. And then they also tested it on group of humans, how it navigates around them. The second paper was published in 2018, which uses motion tracking using Microsoft Kinect and OpenPTrack. The application is basically analyzing motion behavior of humans for a moving robot. And the next one was published in 2019, which uses Gaussian distribution for layered cost map architecture. The application is navigation of service robots in daily life. And the next paper was published in 2020, which used reinforcement learning, reverse reinforcement learning for its model. And the application was delivery robots in indoor spaces. The next paper was also published in 2020, and the method used was deep state representation and classic Dijkstra algorithm. Application was social robot in assistive living environments. And the next paper was also published in 2020, which used long-term motion prediction and A-star algorithm for shortest path. And the application was service robots in indoor environments. Our first paper is a survey on human-aware robot navigation. Problem description. Given the current growth and innovation in the research communities concerned with the topic of robot navigation, human-robot interaction, and human activity recognition, it seems like this might soon change. Robots are increasingly easy to obtain and use, and the acceptance of them in general is growing. However, the design of a socially compliant robot that can function as a companion needs to take various areas of research into account. This paper is concerned with the navigation aspect of a socially compliant robot and provides a survey of existing solutions for the relevant areas of research as well as an outlook on possible future directions. Proposed method. This survey will consider active vision, robot navigation, human-robot interaction, and human activity recognition, as well as their possible overlaps. Previous surveys focused on comfort, naturalness, and cultural convention, type of mapping that was used for navigation. The aim with this work is to give a more general overview and highlight the interdisciplinary nature of the topic. As you can see in the image, socially aware robot navigation can be divided into four categories, that is active vision, visual robot navigation, human-robot interaction, and human behavior analysis and modeling. Under each section, they are further divided into the types in which they are categorized. In human behavior analysis and modeling, pose estimation, action recognition, action forecasting, trajectory forecasting are the components. In active vision, the components are active learning and active perception. In visual robot navigation, the components are map-based versus mapless, and the different algorithms used and the tasks for the visual robot navigation. In human-robot interaction, the components are proxemics, healthcare, industrial context, healthcare context, and social context. Evaluation experiment. So the evaluation experiment they did is based upon the formalized evaluation strategies. Unlike goal-oriented robot navigation or trajectory prediction, socially aware robot navigation is difficult to evaluate in terms of objective metrics. Not only does the robot have to perform a certain task, but the positive or negative effect it has on human sharing the space has to be taken into account as well. So for that reason, the strategy they implemented is they ask the users to rate the behavior in terms of subjective quantities such as naturalness or comfort. Alternatively, another way of evaluation is to check whether it can perform basic subtasks that are required in daily interactions. Contributions and limitations. Since this is a survey paper, as part of contributions, they found a variety of promising approaches and datasets that aim to solve the complex problem of socially aware robot navigation. This paper also gives an overview of the datasets and frameworks. One of the limitations is no possible way of comparing different methods using objective metrics. Paper 2 is on the topic social path planning, that is generic human-robot interaction framework for robotic navigation tasks. Problem description. If the common path planning approach are applied in human-robot environments, the robot will execute movements that might well distract humans, making them feel uncomfortable. Also, if the task of the robot is to interact with humans, the robot should be able to gracefully approach humans and enter and exit their conversational circle without alarming or distressing them, while signaling its intention in a human understandable way. Proposed method. This paper formulates a generic framework for the social path planning problem. They propose a mathematical formulation that can be considered as preliminary step towards a general theoretical setting. This formulation considers the previous formulation available in the literature, but an important novelty is introduced. The social path planning is divided into six different subproblems. By correctly combining these subproblems, most of the navigation tasks for the social robot can be modeled. Now, what are the six different subproblems? So these are also categorized into two. One is single human, which has three subsections. One is robot to point. Here we use regular path planning and consider humans as obstacles. The second is full interaction, and the steps are approach human, interact, keep interaction, and disengage. And the third one is follow human, and Under the second category, that is group of humans, we again have three sections, that is robot to point, which uses regular path planning considering humans as obstacles. Second, observe group, ask for permission to enter. Third is full interaction, that is enter the group, interact, keep interaction, disengage. Evaluation experiment. Here, they integrated their proposed formulation into fast marching squares for path planning algorithm. As you can see in the figure 7, the people are spread out, and once a goal location is given, you can see that it is passing like a little bit away from the humans, and you can see a black spot around the humans, that is the proximix, and you can see the velocity profiles in each color. In red, as you can see, towards the point where it reaches close to human, the velocity drops, and in blue as well you can see a drop where it is too close to the human. And on the right side, that's in figure 8, you can see there is a group of human. So the proximus, which is shown in black color, is the area which the robot has to avoid. So when given a goal location that is towards the left, the robot takes a path which is outside the proximus. Contributions and limitations. Some of the limitations are where, let's say the robot is in very tight space where a lot of humans are there, or it's a very crowded place, it becomes very difficult to navigate and it has to go through the human space. Another limitation is basically a strict application of these rules can decrease optimality in robots and robot behavior. Some of the contributions are generalization of their model to group of n people, and the other one is novel classification as well as mathematical formalization of all the different cases that can be given while navigating close to humans.
Hello everyone, my name is Nihal and now I'll be talking about the third paper, which is Learning Human-Aware Robot Navigation from Physical Interaction via Inverse Reinforcement Learning. Problem description. This paper investigates the force control as a natural means to interact with a mobile robot by pushing it along the desired trajectory. They have employed inverse reinforcement learning IRL to learn from human interaction and adapt the robot behavior to its users' preferences, thereby eliminating the need to program the desired behavior manually. Proposed method. In this paper, they propose to learn the parameters of navigation cost function through physical human-robot interaction. To this end, they formulate a cost function that balances social space preferences and the desire to reach a goal destination. In the right figure, you can see that a woman is pushing a robot away from her to show that the robot is not welcome in her space, and the robot learns this behavior and adjusts its path using reinforcement learning. Evaluation experiment. For the evaluation of this experiment, they recruited 13 test subjects, 5 female, 8 male, between the ages of 21 to 63. None of the participants were involved in the research project or had prior knowledge of the research aim. 8 of the participants had technical background, 2 female and 6 male. 6 had previous experiences with robots, 2 female and 4 male. The experiments took place in the hallway of a building with force-sensitive mobile robot Canny. Now Canny is uses 6 degrees of freedom force torque sensor. Each experiment lasted about 45 minutes. The participants were given 2 tasks with the robot. In one of the tasks, the participants were told to control the robot via force feedback, and for the second task, they were given a joystick as the controller. Now for the first task, the obstacle course task, they performed a calibration task to compare the ease of use and intuitiveness of both control modalities without the robot learning or moving autonomously. For this task, the participants controlled the robot through an obstacle course. And for the second one, which is passing task with inverse reinforcement learning, the passing task tests force and joystick feedback for interacting with an autonomously navigating robot. The participants stood in the center of the hallway and guided the robot past themselves, either via a joystick or by pushing on its shell. They instructed the participants to adapt the robot path like they would prefer it to autonomously drive past them. Before the actual passing task, the participants performed two practice tests to familiarize themselves with controlling the autonomously navigating robot. Firstly, the robot moved in a straight line from start to goal, and the participants freely deviated it from its path to test the behavior. Secondly, they arranged four traffic cones as obstacles and asked the participants to guide the navigating robot around them to ensure they were able to test the behavior and control the robot along the desired trajectory. For the control modalities, the robot initially navigated autonomously from start to goal without considering the person in the hallway. In the force feedback test, the robot iteratively adapted its navigation behavior by optimizing the navigation reward function presented. Questions asked by the researchers were like, was it easy or difficult to control the robot? How much did you like the type of control? Did you find this type of control intuitive? Was the interaction comfortable or not comfortable?
Hi, this is Denny, and I'm gonna talk about the paper 4, that's towards social acceptable human-aware robot navigation. Problem description. The introduction of service robots in our daily life is growing day by day. Hence, the need for intelligent mobile robots to be able to navigate in dynamic environments where the presence of humans is expected. Furthermore, a robot should not only carry out its tasks efficiently but also human-friendly way, adapting its behavior according to social conventions. Proposed method. This paper proposes a layered cost map architecture that incorporates social norms to generate trajectories compatible with human preferences. The implemented framework creates a social abstraction layer of the environment in the form of an occupancy grid to plan human-friendly paths. It employs information about individuals in the scene to model their personal spaces. In addition, it uses predicted human trajectories to improve the efficiency and legibility of the robot trajectory. Evaluation experiment. Evaluation experiment is divided into two parts. One is simulation experiment, the other one is real experiment. In simulation experiment, the first one is two static humans having conversation and we find out what path the robot takes. Uh, as you can see in the bottom left image, the first one, that is the B part, human aware, and navigation is used, and the red and the blue are the two humans which are talking to each other, and the robot takes a path which is not interfering with human space. And the C part, that is default, you see that uh, human aware navigation is not used, and the robot takes a path which is the shortest and it interferes with the human space. And the next part of simulation experiment is three humans in which two are having conversation and the third one is moving. That image is depicted just right to the previously explained image, and you can see the B part, that is human aware, in which top red and just below that there's a blue human, and those two are having conversations, and the third human is actually walking downwards and depicted with a straight line, and the robot takes a path which actually doesn't interfere with any of the human space, and it actually crosses after the human has crossed the uh, navigation path which actually intercepts with the robot navigation path. And on the right side where it uses the default navigation planner, the path it takes actually interferes with the human space, and you can see a lot of weird motions up and down. Now going to the real experiment, the first part is human standing in the middle of a corridor looking at a painting in the wall. So the left part, so this output is depicted in the top right image, where the left part is where there is no uh, human aware navigation planner, and you can see it crosses between the painting and the human, and it is blocking the human vision. But when we use human aware navigation, which is shown in the rightmost image on the top, you can see it takes a path which is away from the human and painting space, so it doesn't block the human's vision. And going to the next point, that is, it involves two persons standing in front of the robot. And what normal planner does is that you can see that image which is on the bottom right. On the left side is default planner without any human aware navigation, where the robot takes a path which is in between the two humans, and on the right side of it you can see the human aware navigation, in which it takes a path which is away from the two humans and it is not blocking their conversation. Contributions and limitations. In this paper, the contribution is basically layered cost map suggested have been integrated into the current version of ROS navigation stack. And the limitation is it depends on robustness and reliability of perception system capable of detecting the pose of multiple of humans.
Hello everyone. Now we're going to talk about paper 5, which is pedestrian robot interaction experiments in an exit corridor. Problem description. With the rapid advances in the development of autonomous mobile robot technologies, the applications of service and socially assistive robots have been woven into people's daily lives. As robots are performing tasks where humans are being involved, the problem of human-robot interaction is present. HRI is studied and considered for human-aware robot navigation, where traditional motion planning approach is amended to respect the effect of HRI on human behavior in the presence of mobile robot. In addition to considering the human being as moving obstacles criteria, such as human confirmed natural motion and socially adaptive motion are taken into account for robot motion planning. This paper they present the empirical study of pedestrian-robot interaction in an unidirectional exit corridor. They deploy a mobile robot moving in direction perpendicular to that of the pedestrian flow and install a pedestrian motion tracking system to record the collective motion of the group. They analyze both the individual and collective motion of pedestrians and measure the effect of the robot on the overall pedestrian flow. Evaluation experiment. The experimental results show that in an exit corridor environment, a robot moving in direction perpendicular to that of the unidirectional pedestrian flow can slow down the unidirectional flow. And the faster the robot moves, the lower the average pedestrian velocity becomes. Furthermore, the effect of the robot on the pedestrian velocity is more significant when people walk at a faster speed. Now, let's talk about the first topic, which is passive pedestrian-robot interaction. They empirically study the regulation of human flow velocity in an exit corridor using interactive robot. As shown in the figure 1, a single interacting robot is added to the pedestrian flow and moves in the direction perpendicular to the pedestrian flow with a pre-designated speed. Since the robot's movement is in the way of the pedestrians towards the exit, the pedestrians see the robot and avoid potential collisions by either changing the speed or altering the trajectory of their own. The pedestrian flow is regulated through the effect of passive HRI. Hypothesis is that the speed of the robot moving in direction perpendicular to the pedestrian flow will affect the average speed of the pedestrians moving through the corridor. The goal of the study is to test this hypothesis, measure the effect of the passive HRI by adjusting the robot's speed on the pre-designated trajectory, and compare the effect with the case without the robot. And when it comes to experimental setup, the environment is the experiment was conducted in the Stevens Institute of Technology in 2016. A pedestrian tracking system deployed in the building covers a 10-meter by 4-meter tracking area as shown, with an exit door at the end of the area. The boundaries of the tracking area are marked with red duct tapes. The tracking system consists of 5 Microsoft Kinect sensors, 6 computers connected to local area network, a pedestrian detection and tracking software. OpenPTrack is used. OpenPTrack is a real-time distributed people detection and tracking software capable of utilizing RGBD images from the Kinect network. OpenPTrack runs on robot operating system. Results: they have recorded pedestrian trajectories using OpenPTrack software and video recording system. They have observed the HRI behaviors when people get close to the robot. It appears that the pedestrian motion behavior changes according to their anticipation of potential collision with the robot, and the density of the area, and whether there's room to move around. They have observed that the speed change of the robot affects humans' motion. On the figure to the right, which is part A and part B, show that the trajectory of the pedestrians interacting with the robot, respectively. The circles and stars represent the position of the pedestrian and the robot at every 1 second. The arrow represents the velocity with the length proportional to the velocity magnitude. From figure A, one can see that the pedestrian adjusts his or her walking direction at around x is equal to 4.5 meters to avoid the robot, as he or she foresees potential collision with the robot. Meanwhile, the velocity of the pedestrian changes slightly. One can see from figure B that the pedestrian adjusts his or her walking direction around 4.6 meters and 5.8 meters respectively, and meanwhile slows down and the collision to avoid collision with the robot. In figure C, you can see that the trajectories of the pedestrian and the interacting robot, from which one can see the pedestrian adjust his or her direction at around x is equal to 4.8 meters, and the results demonstrate that both the trajectory and velocity of the pedestrians can be affected by HRI. Paper 6: Human-Aware Robot Navigation Based on Time-Dependent Social Interaction Spaces, a use case for assistive robots. Problem description: the use of social robots in assisted living environments for older people will become a reality in the coming years. Currently, there are many situations in which human-robot collaboration is demanded. In a caregiving center, for instance, possible scenarios include physical or cognitive activities proposed by assistive robots. The accompanied side by side of the elderly person while walking, clinical staff support. In these situations, planning and following paths in a social aware fashion is essential to achieve social acceptability. This article presents a first approach to the idea of time-dependent social mapping, where the planning of the social route by the robot takes into consideration variables that depend on the time and schedules of certain spaces. To this end, the article describes how human spaces of human-object interaction vary as a function of time and how this affects the social navigation planned by the robot. Several use cases have been performed in a simulated environment to assess the improvement in the robot's social navigation using temporal variables. In the above illustrative example, the object table is not always being used. In fact, its use depends on therapeutic session schedule. In figure B represents the second situation where the robot plans a different trajectory based on the activities schedule without the risk of invading the object affordances. This work uses a shared representation of the environment, which is Deep State Representation (DSR), and the Cortex Cognitive Architecture. DSR is a multi-labeled graph that defines the information of the environment, rooms, humans, objects, as well as the robot, among others. In this graph, nodes are the elements and arcs are the relationships between them, that is, in connected, etc. The overview of the proposal described in figure 3. The social path is planned by using classical Dijkstra algorithm that uses a free space graph of the environment. In this graph, the weights of each node depend on the social map generated by the cognitive architecture. This social map is built by the social navigation agent according to a DSR, which has previously been provided by two different agents, the human observer agent and the object recognition agent. Socially acceptable path planning algorithm, which is Dijkstra algorithm. And this section describes the social path planning algorithm proposed in this paper. Robot's environment is represented in a uniform graph composed of obstacle-free nodes that have a constant finite traversal cost and non-free nodes which have an infinite one. The approach described in this work modifies the costs according to the social map. This final graph is used to estimate the optimal path using Dijkstra algorithm. In the grid-based grid mapping, the classical Dijkstra algorithm is employed for determining the shortest path between the initial position and the target to which the robot must travel. Giving a node of origin, the algorithm calculates the cost of the origin to the target node, taking into account the cost of nodes. The cost of a path is sum of the cost of the nodes that compose it. In the social graph-based grid mapping, the free space graph is modified to include the social space interactions. Firstly, those associated with the interaction between one person and another, or a group of people. And secondly, those associated the interaction between people and objects. Evaluation experiment. A set of simulated caregiving scenarios have been used to validate the results of the proposed social navigation system. In order to assess the validity of the proposed navigation approach, the methodology has been evaluated according to the following metrics. 1. Average minimum distance to a human during navigation, which is d minimum. Distance traveled, which is dt. Third, navigation time t. Fourth, cumulative head changes, CHC. 5 is personal space intrusions, phi. These metrics have been already established by the scientific community, hence it is a standard. The first experiment illustrated in figure 7 and evaluates the first approach described in this paper for building time-dependent social interaction spaces. In figure A physical therapy room with 3 objects is shown: a TV, a circular table, and a stretcher. Previously, the activity scheduling for this room had been set by the center's professionals. In figure B and figure C and figure D, they show 3 different instant times of the social interaction spaces of the objects. As appreciated, the cost of the graph is different according to the activity's agenda. The second test represents a more complex scenario composed of different rooms, objects, and people, and where the activity scheduling is also modified. The robot plans a social path from its current pose in another room. Contributions and limitations. Contributions. Model the system that improves robot social navigation in caregiving environments, with the limitations that's only tested in simulation, unsure of its working in real life, and acceptability of the planned path by humans. Paper 7. Human-aware robot navigation by long-term movement prediction. Problem description. As robots become ever more present in the human environment, so does the need of human-aware navigation policies. To be able to provide a real benefit for humans, a robot should coexist with them without causing discomfort. One common way to achieve this is to mimic human social behavior. A prerequisite for this is the ability to predict human movements and foresee and avoid situations in which the robot could violate social constraints with its navigation policy. Proposed method. In this paper, they presented a novel human-aware navigation approach that relies on long-term prediction of human movements. In particular, they consider the problem of finding a path from the robot's current position to the initially unknown navigation goal of moving user to provide timely assistance there. The navigation strategy has to minimize the robot's arrival time, at the same time comply with the user's comfort during movement. Our solution predicts the user's navigation goal based on the robot navigation observations and prior knowledge about typical human transactions between objects. Based on the motion prediction, they then compute a time-dependent cost map that encodes the belief of the user's positions at future time steps. Using this map, they solve time-dependent shortest path problem to find an efficient path for the robot which still abides by the rules of human comfort. Figure 1 depicts an application example of their approach. As can be seen, the robot chooses a path to the user's predicted navigation goal. It also tries to minimize discomfort of the humans by avoiding the direct route, which interferes with the human's path. To summarize, the contributions are as follows. Number one, a human-aware navigation system based on long-term movement prediction, human comfort constraints, and path planning on a time-dependent cost map. Second, the conduct of a survey about human comfort to evaluate different navigation strategies. Third, an evaluation of the complete system in terms of arrival time and human comfort in comparison to state-of-the-art methods, both in simulated environments and predefined metrics, and in real-world experiments with direct human feedback. Evaluation experiment. According to the proxemic theory, humans have personal space regions around them, in that others, including robots, normally cannot intrude without causing discomfort. The size and form of these regions depend on the familiarity of the intruder. Example, a friend is allowed to move closer to a person than a stranger. To model than a stranger. To model the allowed proximity of entities in an unfamiliar social context, the social zone (SZ) is used, which is circular interpersonal space region around the human with a radius of 1.2 meters. As a service robot, it represents a typical example of an unfamiliar entity inside a social context. We model the social zone (SZ) as a minimal distance that the robot must hold to humans. Furthermore, as noticed by another researcher, objects inside a rectangular area with a length of 4 meters and the width of 1 meter in front of moving humans are considered as potential obstacles. This area is called Information Process Space (IPS). Moving inside the IPS does thereby by definition disturb the path planning of humans, and a robot should avoid this area to reduce interferences. To find further constraints, we conducted an interview survey with 8 student participants from the University of Bonn. Each interview lasted around 15 minutes. Participants were asked about their feelings towards service robots, for which tasks they could envision to use robots, how they would design them, and whether there was any behavior that they saw as desirable or undesirable. All participants favored unobtrusive robot behavior. They also had a follow-up survey with 261 participants online. They restricted the survey to German participants to stay consistent with the interview survey and later real-world experiments. They did not have any formal requirements for participants and aimed for a cross-section of further population. In the survey, they asked participants how they would feel about robots following them, which distances the robots prefer to be from them, and how they rate obtrusive robot behavior against efficient working of robots. They found that 61% of the participants did not want a robot to follow them. 57% would accept a reduced work performance if the robot would behave more unobtrusively, supporting the trend of the interview study. Regarding the robot distance, we found that 77% of the participants had no problem if the robot was moving at approximately 3 meters in front of them, as long as the robot did not enter their IPS zone. While only 58% would say the same if the robot was moving at the same distance behind them. However, this number increased to 70% if the robot was at least 5 meters behind the human. Their solution consists of the following steps: prediction of the user's navigation goal by applying Bayesian interface using prior knowledge about the transitions between objects and the knowledge about their locations as well as current observations. Second, computation of a time-dependent cost map based on the predicted user positions at the future time steps and social constraints as described in the previous section. Number three, solving the time-dependent shortest path problem on the given cost map, and executing the returned path. These steps are highly regularly executed to update the prediction and recalculate the best robot navigation action based on new observation. Results. To evaluate the approach, they performed a quantitative evaluation in simulation with 140 trajectories in a real-world experiment in their lab with 11 participants. For the quantitative evaluation, they used metrics by the human comfort, which is HC, and the difference in the arrival time between the robot and the user, delta t. Positive delta t values indicate that the robot arrives at the goal before the user. The higher this value, the earlier the robot will be to the true navigation goal of the human. To quantify human comfort HC, they measure the ratio of the number of robot positions outside the social zone SZ or IPS zone and the robot's overall number of positions as social distance compliant SDC, as well as the average human robot distance HRD. Based on their surveys, an optimal human-aware robot path has an HDC of 1.0 and a high average distance. During the real-world experiments, they asked the participants to rate the comfort with the robot navigation behavior on a zero point 0.5 Likert scale rating, 1 as uncomfortable to 5 as very comfortable. In all the experiments, they compared the results with three existing approaches: the social force approach, which implied a short-term prediction system; a reinforcement learning approach, which uses long-term user prediction, uh, and no time-dependent path planning; and the follow last approach, which used a follower approach, which does not use a prediction system and was configured to follow the user at a distance of 2 meters. Table shows the evaluation results. As can be seen, our approach archives the highest HRD and the second highest SDC and delta T. Social distance violations were mostly encountered when the user moved unexpectedly while the robot was trying to pass them. Typically, the robot would pass by the user as soon as possible and wait at key points of the map to update its prediction. In contrast to that, the reinforcement learning approach focuses on reaching the most likely goal as fast as possible.
Hi, this is Denny. The open research questions are interpretation of a person's intent through machine vision and learning, robot motion based upon a person's field of view, legible and predictable robot motion, how do the robot's speed and proximity affect the person's comfort, link between the robot's size and shape with person's comfort, the appropriate spacing model for a mobile robot, psychological attributes of a person which are influenced by a robot's attribute. These are the references which we used for our presentation. Thank you.